Hello, so this is the part 3 of the lecture about the design and analysis of a single factor experiment. So this part 3 lecture is about the random effects model. Okay, here we will discuss about the random factors and we'll compare it with the fixed effects model. Okay, because in the previous lectures and discussions we already know that fixed effects models or fixed effects factors are factors that are chosen by the experimenter. Okay, the experimenter is the one who chose the labels. Okay, the labels under the treatment. The labels are also called as the factor labels. Okay, so factors, the word factors is synonymous with treatment. Okay, so here we will compare the fixed factors versus the random factors. Okay, because in many situations or in real life situation, the factor of interest has a large number of possible labels. Okay, so we as the analysts, we are interested in drawing conclusions about the entire population of factor labels. Okay, so this like to this like to uh, estimating. Okay, estimating the effects of the whole population. Okay, so a random factor is randomly selected from all level of the population's factor labels. Okay, so that is the random factor, meaning it is not fixed. It is randomly selected from all levels of the population factor labels. Okay, because of this random factor, the conclusions reached will be valid for the entire population of factor labels, meaning because of this random factor, uh, it serves as a good estimate of the whole population factor labels, because here we are assuming that the population of factor labels is either infinite size or large enough to be considered infinite. Okay, because we cannot include all the labels under a factor or a treatment when it is infinite size and large enough. Okay, so this is very different situation compared to the fixed effects case, because in the fixed effect case, the conclusions apply only for the factor labels used in the experiment, meaning the conclusions only apply to the factor labels that are selected, okay, that are selected by the experimenter. So it is very different to the random factor. So this is the ANOVA and the variance components under these random factors. Okay, the linear statistical model or the components of variance, because uh, uh, these variables are the components of variance, and the random effects model. Okay, this serves as the random effects model because we have here a random effects. Okay. So this is very identical. This is identical in structure to the fixed effects case. As you remember, in the part 1 of our lecture, this is identical to that. Okay? So, where the treatment effects, this is the treatment effects, the tau sub I and the errors, epsilon sub ij, are independent random variables. Okay? They are independent and random variables. So if the variance of the treatment effects is tau sub I is, so here we are considering that our variance of the treatment effects, which is the tau sub I, is equal to what? The sigma. Okay? The sigma squared sub tau. Okay? So this is its equivalent. By independence, the variance of the response is this. So this is the variance of the response. Okay? V stands for the variance. And the response is this because this is the dependent variable, the response variable. So its variance is equal to the square of the tau of the sigma sub tau plus the square of sigma. Okay? So the variance says sigma squared sub tau and sigma squared are called the variance components. So here are these two are the variance components. They make the whole variance. Okay. To test the hypothesis in the model, we assume that the errors epsilon sub ij are normally and independently distributed with mean zero and variance sigma squared, and the treatment effects tau sub I are normally and independently distributed with mean zero and variance sigma squared sub tau asterisk. So here are the assumptions. You must remember those assumptions. So for the random effects model, testing the hypothesis that the individual treatment effects are zero is meaningless. So in the random effects, we will not be doing what we did in the fixed effects model, because in testing the hypothesis, this is meaningless. Okay, rather it is more appropriate to test hypothesis about this, the sigma squared sub tau. Okay, so we will test the hypothesis with it. So our null hypothesis is sigma squared tau sub tau is equal to 0, or our alternative hypothesis is equal to sigma squared sub tau is greater than 0. Okay, so here, if the sigma squared sub tau is equal to 0, all treatments are identical. Okay, remember that. Meaning, if we accept or we don't reject the null hypothesis, all treatments are identical. Okay, meaning there are no differences in all treatments. But if the sigma squared sub tau is greater than 0, meaning there is a variability, okay, between treatments. So if we reject HO and this one belongs to the alternative hypothesis, meaning the variability, there is a variability or differences between treatments. So the ANOVA decomposition of total variability is still valid, meaning this equation is still valid because this is the ANOVA decomposition. Okay, so remember this: the total sum of square is equal to the sum of square of treatments and the sum of square of errors. So it is still valid here in random effects. So in the random effects model for a single factor completely randomized experiment, the expected mean square for treatment is, so this is the expected value of the mean square treatment, and while this is the expected mean square value of the error. Okay, so remember those formulas. Okay, so from examining the expected mean squares, so from examining these formulas, it is clear that both the mean squared of the error and the mean square of the treatments estimate the sigma squared, right? Because here you notice that they are equal to the sigma squared. Okay, these two. But here there is a random effects here, the variance of the random effects. Okay, so when HO, or the null hypothesis, or the sigma squared sub tau is equal to 0 is true. Okay, so furthermore, the mean square error and the mean square treatments are independent. Okay, so consequently the ratio, F statistic, MS sub treatments is equal to MS sub E. Okay, so that's how you get the F value, or it is an F random variable with degrees of freedom, A minus 1 and A n minus 1. What is A again? A is the number of levels under the treatment or the factor. Okay, so N is the number of observation or the sample size. Okay, so degrees of freedom, when HO is true, the null hypothesis would be rejected. So we will reject the null hypothesis if if in a given alpha level of significance, what we computed here, what value we come up here, okay, is greater than, okay, with a tabular value. So we will reject HO if that's the case, okay. So the assumption that the tau sub I are independent random variables implies that the usual assumption, remember this, the usual assumption, okay, the summation of tau sub I as I is equal to 1 goes to A levels is equal to 0. Remember this. This is the assumption in our first lecture, part 1. Okay, from the effects, it is from the effects, fixed effects model. Okay, does not apply to random effects model. So, remember that. Okay, because the assumption of tau sub I are independent random variables. So, this assumption is not applicable for random effects model. So, the computational procedure and construction of the ANOVA table, so remember the ANOVA table, the format, for the random effects model are identical. So, it is identical to the fixed effects. Okay? But the conclusions, however, are quite different. Because here in random effects model, it is applied to the entire population of treatments. Okay? Entire population. Usually, we also want to estimate the variance components. So, these are the variance components, remember, in the model. So, we are going to estimate them. The procedure that we will use to estimate these variance components is called the analysis of variance method because it uses the information and the analysis of variance tables. Well, we will only rely in the analysis of variance table in computing this. So, it does not require the normality assumption of the observation. So, even though our observations are not normally distributed, it is okay. So, the procedure consists of equating the expected mean. So, we will equate the expected mean squares to their observed values in the ANOVA table. Okay, we will just equate them. And solving for the variance components. When equating observed and expected mean squares in the one-way classification random effects model, we obtain, so this is what we obtain in the random effects model under the one-way classification, okay, of ANOVA. So, ayan. Mean square of the treatments is equal to, so these are the formulas, okay, the sigma squared plus the number of sample times the squared of the sigma sub tau. And for the mean squared of the error is equal to the squared of the sigma or the variance. Okay. So these are the formulas for the estimators of variance components. As you notice that they have hat. Okay. The sigma has hat. When you observe a symbol with hat above it, it means it is an estimate, okay, estimator, okay. So sigma hat squared is equal to the mean squared error. So it is an estimate, the mean squared error, and the sigma hat squared sub t is equal to the mean squared treatments minus the mean squared error all over the number of sample n. Okay. Sometimes the analysis of variance method produces a negative estimate. Okay, so when you got an estimate of negative, so it is possible. Okay, but since variance components are by definition non-negative, okay, a negative estimate of variance component is disturbing. So it might be affected by some factors. Okay, so this is one solution for that. So one course of action is to accept the estimate. You will just accept the estimate and use it as evidence that the true value of the variance component is 0. Okay, so you will just accept it and use it as the evidence that the true variance is 0 because it is less than 0. Assuming that sampling variation led to the negative estimate. So you will just assume that the reason why you have a negative estimate is because of the sampling variation. Okay. Next, this is another one. Okay, so this must be big letter. So to re-estimate the negative variance component, so second one is you can re-estimate the negative variance component with a method that always yields non-negative estimate. So what is that method? Okay, to re-estimate the negative variance component with a method that always yields non-negative estimate. You will make or you will transform, okay, transform each value so that they will not be negative. Okay, so another one is the possibility is to consider the negative estimate as evidence that the assumed linear model is incorrect. So if you have a negative estimate, you can use that as an evidence that the assumed linear model is incorrect, requiring that a study of the model and its assumptions must be made to find a more appropriate model. So those are the ways that you can use if you have a negative estimate. So let's go now to the example problem number 1. So a textile manufacturing company weaves a fabric on a large number of looms. Okay, so imagine that they have some large or infinite number of looms. Okay, too large to count. Okay, so the company is interested in loom-to-loom variability in tensile strength. Okay, so to investigate this variability, a manufacturing engineer, so it must be you as you are a manufacturing engineer, as industrial engineers, selects 4 looms. Okay, he selects 4 looms at random, meaning he selected a random factor. Okay, random factor, and makes 4 strength determinations on fabric samples. So he used 4 uh, 4 labels. He chose 4 labels and 4 observation or 4 samples chosen at random from each loom. The data are shown in the next table. So these are the data. You will notice that the manufacturing engineer chose 4 labels of loom. Okay, 4 labels or 4 looms at random and 4 observations. Okay, for the strength determination. So you will just total them. Okay, grand total and average of each label. Okay, you will get the average and the grand total of the average. So it is the same procedure. It is the same procedure in our lecture 1 to come up with this. Okay, so the sum of squares is summarized here. So it is the same. The format is the same. So for the looms, you have 89.19 square of sum of squares, degrees of freedom 3, mean square 29.73, and F statistic. So all this value, okay, all this value, you will just substitute, you will just use the previous formula. Okay, you will just substitute them in this formula for the F. Okay, and the other formula are the same. Okay, the same uh, the same from the lecture number 1. Okay, so remember, this 89.19 is the sum of squares of the treatment because it is in the row of the looms. Sum of square of the treatments. While this 22.17 is the sum of square of the error. Okay? So the degree of freedom 3 is, we can get that by uh, subtracting 1 from the number of A labels under the treatment. Okay? So 4 minus 1 is 3. So the error, okay, so the formula, what is the formula for this? So A times the quantity n minus 1. So if you have an n of 4, so 4 minus 1 is 3. So 3 times, what is the A? A is 4, so it is 12. Okay? And to get this mean square, you will just use this formula, okay? The mean square for the treatment and for the error. Okay? You just substitute them there. And for the F value, okay, you have your ratio here. Okay, so that's the F value. the probability value, you can see that when you use SPSS or table, okay, F table. So this is the interpretation. From the analysis of variance, we conclude that the looms in the plant differ significantly in their ability to produce fabric uniform strength. Why do we say so? Okay, because our computed value is large enough. But here, it is the tabulated value is not given. So when the tabulated value is not given, you don't have a value to compare with the computed value of f. So you will just refer to the p-value. If the p-value or the probability value is much smaller than 0.05 or 0.01, okay, it is less than, so meaning we will have to reject HO, okay, and conclude this, okay. Conclude that the looms in the plant differ significantly in their ability to produce fabric uniform strength. So to get the variance components, use the formula, okay. So here is just equal to the mean square error. So these are the formula, okay. 1.90, and here it just is just equals to the difference of the mean square of the treatments and the mean square of the errors all over the number of observations. So it is 6.96. Therefore, the variance of strength in the manufacturing process is estimated by, this is the total variance or the total error. Okay, we will just add these two to get 8.86. So most of this variability is attributed to differences between looms. Okay, they are attributed to differences between looms. Why? Because you will notice that 6.96 is greater than 1.90, and 6.96 come from the what? From the estimator of the mean square of the treatments. Okay? So, another conclusion, this example illustrates an important application of the analysis of variance. So, why it is important? Because the isolation of different sources of variability in a manufacturing process is our concern as industrial engineers. Problems of excessive, okay, variability in critical functional parameters or properties frequently arise in quality improvement programs. So, these are part of the quality improvement program. Another example, okay? In the previous fabric strength example, the process mean is estimated by this. Okay? This is given because it is estimated in the previous example. And the process standard deviation estimated by this. Okay? So why? We will just get the square root, standard deviation. Okay? So 2.98. The square root of what we got here. Okay? 2.98 psi. So if the strength is approximately normally distributed, the distribution of strength in the outgoing product would look like the normal distribution shown here. Okay? So we'll just assume that the strength is normally distributed. So the distribution of fabric strength, this is the current process. Okay? So if the lower specification limit, LSL, so this is the lower specification limit, on strength is at 90 psi, a substantial proportion of the process output is fallout. So this is what you call as fallout, less than the lower specification limit. Okay? It means that it is a scrap or defective material that must be sold as second quality, and so on. This fallout is directly related to the excess variability resulting from differences between looms. Okay? So the variability in loom performance could be caused by a faulty setup. So these are the causes of the variability between looms: poor maintenance, inadequate supervision, poorly trained operators, and so forth. So here, the engineer or the manager responsible for the quality improvement process must identify and remove these sources. Okay, you must identify those sources of variability from the process. If this can be done, the strength variability will greatly reduce. Okay, perhaps as low as this. Okay, So, eliminating those variability under the treatment, okay, you only have, what is this? So, this is the value of the, uh, the variance, okay, or the error, the mean square of the error. Okay, eliminating this, okay, under the treatment, you will just have to consider this, or uh, the error of the normal errors, okay? So, getting it squared, we have 1.38 psi as the standard deviation. As in the figure below. In this improved process, so this is an improved process, okay? So, in the improved process, reducing the variability in strength has greatly satisfied the fallout, resulting in lower cost, higher quality, as more a satisfied customer, and enhanced competitive position for the company. You will notice that all the values here uh, is greater than the lower specification limit. Okay, so there are no rejects because we only consider those mean squared error. Okay, we have eliminated those mean square under the treatments because they are the avoidable error. Okay.